Our speaker today will be Venkat from the Oak Ridge National Laboratory. He finished his PhD at 2014 at Purdue University. After that, he did a postdoc at the Lawrence Berkeley National Laboratory, where he worked at reconstruction for X-ray scattering and tomography. Right now, he is an R&D staff member at the Imaging Signal and Machine Learning Group at Oak Ridge National Laboratory, developing computational imaging algorithms in support of the lab's effort in ultrasound, X-ray, electron, and neutron-based systems. His research is mainly in computational imaging, inverse problems, and machine learning, and he got several awards. Among them, we may name the Presidential Scholar Award at the Microscopy and Microanalysis Conference, the Eugen Wigner Distinguished Staff Fellowship at Oak Ridge National Lab, and he also a recipient of the SIAM Best Paper Award for 2020. He is also a senior member of the IEEE, a member of the IEEE Computational Image Technical Committee, and an associate editor at the IEEE Transactional Computational Imaging. And today he will talk about his research, about pushing the limits of scientific CT instruments using algorithms. So welcome, Venkat.
Hey, thank you, Raja. Thank you for the introduction. I would like to begin by thanking the organizers for giving me this opportunity to present here in this unique forum, since we are not able to meet. And thank you for all, for signing in. I recognize there are people from vastly different time zones. So for those of you who are signing in very late, particularly, thank you. So I'm Venkat, as Raja work as scientist at Oak Ridge National. And today I'll present some research on scientific CT. So before I dive into the talk itself, I would like to acknowledge several wonderful collaborators. So we are a research lab where we have collaborations. It's a very interdisciplinary environment. So I'll begin by acknowledging my collaborator Amir, who's actually on the call, who will be available to take questions as well at the end. Jacob, Vincent, and Philip from the imaging side, and we closely collaborate with researchers in our manufacturing sciences, in our nuclear sciences, biosciences, and a lot of collaboration with researchers in neutron sciences at the lab, and including external collaborators at NASA and Iowa State. So I would also like to acknowledge the funding that has made this work possible from the Oak Ridge Laboratory Directed Research and Development Program and the Department of Energy's Office of Energy Efficiency, Renewable Energy, as well as the Basic Energy Sciences. So all this would not have been possible without generous funding and wonderful collaborators. So just so that everyone is on the same page, today's talk is going to be about computed tomography, or CT in short. And at a very abstract level, you have a source of electromagnetic radiation that interacts with a sample, and you make a measurement of that interaction. And the goal is to be able to image inside of an object. And typically, you have the source interacting with the object, and you either reorient the source and detector or reorient the object, collect several measurements, and then feed it to a reconstruction algorithm, which then produces a digital, a digital rendering, a digital realization of the object. And therefore, you can probe individual slices. So today's talk is going to focus on the reconstruction algorithm side of this chain. So why is this very popular in sciences? So CT is actually a workhorse tool in sciences. And one of the most relevant recent examples is some type of tomographic technique is used to image, for example, viruses, or a lot of biological macromolecules. So this is a rendering from authors who have studied the COVID-19 spike protein and imaged it at almost atomic resolution. And it's really incredible that people can do such things. There is, CT is used for nanoscale imaging as well. So for example, here is an example where they've looked at imaging battery materials and to understand how batteries degrade at the nanoscale. Here is yet another example of microscale imaging of a nuclear fuel material. And what you can see are damages that are occurring on the outer cladding. And the point of these characterization tools is that it helps scientists understand something about their material so that they can go back and modify the functionality and then repeat. So it's a very critical, CTs in sciences is a very critical piece in establishing structure to function relationships in the sciences. And the amazing thing is there are tools available to do CT starting from the atomic scale all the way up to the micron scale. So CT is really important. There are several tools that are used to carry out such studies and renderings that you see here. So some popular instruments to do CT are, one of them is electron microscopy. So you have an electron beam interacting with a sample and a detector that measures a single image. Now, in order to do CT, while a lot of you may be familiar with electron microscopy, in order to do CT, these microscopes have been now fitted with holders that can tilt or rotate the sample. And you can collect data which looks like this. And then once you have data like this, you can feed it to a reconstruction algorithm. And then you can do, 3D, you can go and probe your object in 3D. So for example, this is work done at Oak Ridge by some colleagues of mine who have been studying nuclear graphite. They're studying irradiating a graphite and at the nanoscale, and they're able to identify that there are some cracks that occur at the nanoscale. So it is quite remarkable that you can start really looking at objects at the nanoscale with such an instrument. Yet another instrument that is used, of course, is Xray CT. So people from the medical field are quite familiar with Xray CT, but there is a similar thing, principles using scientific CT. So there are two popular ways of, again, doing CT with X-rays. One of it is you can buy a benchtop type instrument where you have a cone beam which interacts with which is shown on the sample, and you have a detector assembly. And then you can collect data. So for example, we're looking at jet engine turbine blades that have been additively manufactured. And then you can collect data, CT data, and then do reconstructions and look at defects, damage that might occur due to the manufacturing process. Yet another popular way of doing CT is using synchrotron. So for those are electron beam. It's basically an accelerator. So you have an electron beam that is circulating here, and at every bend, it produces an extremely bright source of X-rays. So compared to the instrument on top, you basically have a very high flux that comes out of each of these. And there are synchrotrons across the world these are just two images, one from Brookhaven National Lab in the US, and this is the Paul Scherrer Institute in Switzerland. And just if you've never seen one of these instruments, right here, what it really looks is there is a guide pipe that brings in X-rays, and then you have a sample stage where you can mount your sample and rotate it, and then you have a detector assembly. So these are pretty large instruments, and the goal is that scientists across the world can write proposals for ideas for things they want to measure, bring it here, and then conduct scientific studies where you can collect data sets, which are essentially tilt series data sets. And then once you've looked at the sample from different orientations, then you need reconstruction algorithms to do the final 3D reconstruction. So X-ray CT is again a very popular tool in the sciences, both at synchrotrons as well as benchtop. Yet another instrument that is used is Neutron CT, and this is unique to some facilities. Oak Ridge is one of them. So producing a high flux of neutrons is not very easy. So at Oak Ridge, we are home to something called the high flux isotope reactor, which is one of the highest flux research reactors in the world. And once again, the principles are similar. Once you generate neutrons, there are guide pipes. Here again is a cut open of what it would look like inside. You have a guide pipe that brings neutrons in, and then the samples are mounted here, and then you have a detector assembly that is used. Now, neutrons can also be produced by something called spallation sources, where you have, again, an accelerator. Proton beams are produced, then they strike a mercury target, and it spalls, and you get pulsed source of neutrons. So there are different sources. These are also very sophisticated instruments, and a lot of ingenuity goes into building such an instrument, right? But today's talk, I'm going to focus more on the algorithmic side of that chain. And again, Neutron CT is needed or is used for very interesting applications. So for example, here is a little biofuels applications where plant biologists at Oak Ridge are interested in studying plant root systems, and they're able to do so in 3D using Neutron CT. So here's a little 3D rendering of the root system of this plant, which was used to study. So the bottom line is that these instruments play a vital role in the scientific discovery process, and there are a variety of them. So if I have to step back and look at what challenges there are in obtaining high quality reconstructions from such instruments, The first thing that can happen is that the physics of image formation can be complicated. So in many popular CT applications, you can assume linearity in your forward model, or you can pre-process the data so that you're left with solving a linear inverse problem to some extent. But when you have an instrument that is open to everyone, there are classes of samples that people might bring, which break some of those assumptions. And therefore, if you just plug in standard reconstruction algorithms, that is going to result in reconstructions with a lot of artifacts. So that is one of the first challenges that occurs in these scientific CT applications. The second is that these instruments are not optimized for a specific sample type, right? So it's not like building a medical CT scanner that is pretty, it's going to be repeated for the same kind of use, and there's also mass produced. So these are not mass, especially the synchrotrons and the neutron type facilities. These are sort of unique facilities, and therefore these instruments are not really optimized for one thing. They need to be flexible enough so that scientists can try out bold new experiments with CT. So as a result, the real data that you get is often noisy. And it can have a lot of other artifacts, which we'll go into more details later. The other challenge in scientific CT that I have observed is that the data sets can be very large due to the fast, high resolution detectors. So therefore, you're often looking at detectors which are at the very least, not at the very, but they can go from 1K, 1000 by 1000 for each image to 2K by 2K to 4K by 4K. And the scientists are often pushing the limits of these, of these detectors. And so when we as algorithm developers, we have to be able to keep up with that and write code where we're able to get reasonable reconstruction speed. The final challenge is that there's a tendency right now to collect a lot of data, because often the algorithms that are available for reconstruction are very conventional ones that may come with popular packages. And that results in long times, which can again be a challenge when your facility where the goal is to maximize the throughput, allow as many people as you can to conduct experiments. Something like this can be limiting. And therefore, there is a need for new algorithms to be developed in order to address these challenges. So with that, CT is, of course, not a new topic. There are several algorithms out there. And at the core of the reconstruction problem, we're looking to solve an inverse problem. That is, you have something you want to measure. You have a physical system that makes a measurement. The measurements are noisy, impacted by a lot of other imperfections. And the goal is to go backwards and estimate the unknown quantity. So the two popular methods that are used, one is based on analytic reconstruction techniques, where you essentially have some kind of a formula which can quickly get you the answer. These are simple and fast techniques. They have better noise resolution properties, are slightly better understood, but they can result in artifacts for complicated scenarios that we saw in the previous slide. Now, I'll say that an overwhelming number of papers, if you go and scan the literature of scientific CT and start looking at the methods section and look at what methods are used for reconstruction, an overwhelming number of papers still use the analytic reconstruction techniques because they're fast, simple to use, and part of it is a little bit of inertia, right? This is what has been around for a while. People understand them, and they're used a lot. Yet another class of techniques is model-based image reconstruction techniques, where we cast the reconstruction as minimizing a cost function with two sets of terms. The first one is the data fidelity. The second one is the regularizer. And I think for this audience, many of you know that this can be equivalent to the map estimation, where you have the log likelihood and the log prior. Essentially, for those of you who are not familiar, you're minimizing a cost function. The first term encodes the physics and the noise characteristics of the detector. The second term encodes some type of regularization and therefore enforces some kind of desirable properties on the reconstruction. These techniques have gotten very popular. And we've had multiple talks in the past also in the series on techniques like this. And the nice thing is with model-based methods, is you can put in complicated physics-based models, or you can account for complicated physics. It works well with high noise, sparse view type scenarios. On the downside, these methods can be computationally very expensive, and you can also get significant artifacts when your models are mismatched. So today's talk, in the first part, we're primarily going to focus on bringing these type of techniques to scientific CT applications. So the outline will be the first part of my talk. We'll discuss model-based reconstruction algorithms in the context of a few interesting scientific CT applications. We'll begin with Neutron CT and specifically hyperspectral. And then I'll just briefly give you some highlights of work we've been doing on CT with unconventional geometries and also some cone beam CT for some challenging materials. In the second part of the talk, we will look at some direct deep learning techniques. So again, that there is still, there is still something to be said about techniques that produce reconstructions almost instantaneously. And so the direct deep learning techniques are an attractive candidate. And so we'll present some work on bringing these techniques towards a scientific CT for doing efficient Neutron CT and some cone beam CT. So with that, let's begin on the first major topic for today, which is the model-based reconstructions for Neutron CT. So why Neutron CT? So many of you might be familiar with X-rays, but neutron imaging is somewhat unique. And it's very interesting because the contrast mechanism for neutrons is the nucleus of the atom itself. So if I look at X-ray cross sections, hydrogen may not attenuate much, whereas an element like iron will attenuate strongly. Whereas in neutrons, something counterintuitive happens, maybe if you've not thought about it, but is that elements like hydrogen can attenuate significantly, right? That's why water is used as a moderator in a reactor. Whereas something like iron might be less attenuating than that. And that causes that interesting fact causes different contrast mechanisms. So this is an image from the Paul Scherrer Institute in Switzerland, where they've imaged a Buddha statue with X-rays and neutrons. So this is a single radiograph, and you can see a very different type of features with both, right? So you cannot see organic materials very well with X-ray CT. It's very less contrast, whereas with the neutron imaging, you can clearly pick up all this organic material. You can see that there's a little post of some sort, maybe, which holds the thing together, which you cannot see with X-ray. So it's a complementary technique. It has a very high penetration power for heavy elements. It's sensitive to hydrogen and can also be used to discriminate between different isotopes, for example. So that is one of the motivations for why people are interested in neutron imaging in the first place. Now, there is one type of neutron imaging, which is hyperspectral neutron imaging, which is these are accelerator sources which can produce pulsed source, which is a pulse neutron source. And the nice thing is, you can, by using a pulse neutron source along with a time of flight detector, you can essentially do wavelength resolved imaging. So, if I were to look at this little block of metal, for example, using a white beam, which is not energy discriminating, you might get an image like this in a radiograph. Whereas if you step through the different wavelengths and image them at different neutron wavelengths, you can start seeing patterns. In this case, the DOE for the Department of Energy. And basically, this because some parts of this elements were engineered to have a different crystal structure, which diffract at certain wavelengths, and you can start looking at this. So this gives you an idea of why wavelength resolved neutron imaging is interesting, why it's important to material scientists. So the wavelength resolved neutron instruments they're based on a pulse source with a time of flight detector. As I said, whenever you have a hyperspectral imaging modality, one popular application of it is chemical mapping, right? So often CT provides structural information, but so similar to those cases, even with wavelength resolved neutron CT, it is used for structural mapping of materials, where you can look at different chemicals having different signatures, and you can do CT with that. Now, another interesting class of materials that is used in wavelength resolved neutron imaging is crystalline materials. So these are materials that can diffract using Bragg's law. That is, whenever the wavelength satisfies the crystallographic, and the crystallographic spacing satisfies this condition, and lambda is 2D sine theta, you get a strong diffraction. And often this makes it hard to do CT with these materials. So while you can do imaging, when you start doing CT, there is something very challenging that occurs. So the summary is that when we have wavelength resolved neutron imaging and want to image crystalline materials, that is not easy to do. And here is a more precise reason for why that is true. So here is a single voxel. Think about a single piece of a material that you're imaging through in transmission, and you're measuring the attenuation coefficient as a function of wavelength and the rotation angle. So typically, in standard CT, when you rotate an object, the linear attenuation coefficient of the voxel does not change as a function of rotation angle, right? So that's one of the foundational assumptions. However, when you have a single crystal material, that is not true. So what you're looking at in this picture, for example, is the attenuation coefficient as a function of angle and wavelength for a pure crystal. And you can see that as the crystal is rotated, if you fix a certain wavelength, at certain angles, you're going to get a sharp spike in the attenuation because in the transmission direction, because the beam diffracts strongly. So this makes it very challenging to do CT because the attenuation is essentially changing as a function of the rotation angle. But the nice thing is this can be sparse. That is, it only changes at a few locations, which we can exploit when we try to build algorithms for such cases. So so that is one of the challenges, that you can have an attenuation which is a function of angle. The other challenge with wavelength resolved neutron CT is that these are extremely time-consuming measurements. So the flux, the detector efficiency and low flux in neutron CT make it very challenging, and it can take a very long time. So a standard CT scan, for example, can take, for example, we did a CT some recently, and it took 3 days to acquire about 30 angles, projection angles. So this is a very extremely time-consuming measurement, and further complicated by the fact that when you're looking at crystals, you can start seeing diffraction. And what you're going to see now is that when you're rotating the sample, this is all simulations, at certain angles, it flickers. And the flickering occurs because the attenuation suddenly changes. So in order to get around this, we've developed a framework which first involves doing a tomographic reconstruction. But the reconstruction is done so that we are able to not just do a reconstruction, but also identify measurements which were impacted by this Bragg scatter. And once we do that, we can do something more. We also went ahead and said, oh, once you're able to do this, we can go ahead and relate each of the domains in the 3D object and say when it went into the Bragg condition. So you get this binary indicator using this proposed approach. So how do you do a tomographic reconstruction from such data, right? Because it's diffracting very strongly, and you have this transmission data. So the key piece of doing the tomographic reconstruction is to use something what we call a robust model-based iterative image reconstruction approach. So in this case, you can imagine we're doing reconstruction for a single wavelength for now. And the whole idea is that we are going to formulate the cost function, and the first term is based on a Huber-like penalty. It's based on a Huber-like penalty applied to the projection, right? So you have the forward op on the 3D object at a certain wavelength, and this is a weighting function, which is in transmission tomography typically set to the counts itself. And for the regularization, we use a standard regularizer. So that is the key contribution. We said that when we have this type of data, it might be useful to put a different type of cost, forward model that effectively removes the influence of large measurements that don't fit the forward model very well. So we're kind of doing like a band-aid solution where instead of adjusting the forward model, we're adjusting the penalty term so that we can reject measurements which are due to the crystalline nature of the sample. And once we have that, we have a cost function which we have to minimize. Now this is a non-convex problem. So what we do is we use a surrogate function approach where we start with an initial guess, build a quadratic surrogate at that point. So the surrogate is equal to the original function, and it upper bounds the original function at every other point. And we minimize the surrogate, and it guarantees that you have a sequence of decreasing cost values. And it turns out, if you think about surrogate in this case, the surrogate function has a simple form. It's either quadratic if the initial point is less than a certain threshold, and it's just a constant if you are beyond that. And if you go ahead and plug that into the original cost function, so instead of the Huber penalty, you have the surrogate function, which has a parameter t, and it's based on the current error. So you start with the reconstruction, project it, find the error between the measurements and your reprojection. And if that error is very large, you essentially reject that measurement in the next inner iteration. If it's small enough, where small is defined by some threshold, you set it to the original weight. And essentially, by using this kind of penalty, we've turned the problem into a sequence of weighted least squares, regularized weighted least squares type problem, where the weights are changing on the inner iterations. And once we have this, there are a whole host of tools. We have just used some first order methods to do the inner minimization based on optimized gradient method. So the nice thing is we can now start handling crystalline materials. And here is an example of a reconstruction of the sample we saw earlier. And you can see that the MBIR reconstruction, we are able to actually clearly see the letters DOE, which is what the sample was composed of. And the nice thing is we are also able to, at the end, identify which measurements itself were impacted by this Bragg scatter. Now we've gone ahead and then you can go back and then start correlating each of the individual domains to the backscatter events. And you can say, okay, if I can segment out, take the 3D reconstruction, segment out, chunks, I can now say when it went into the Bragg condition. So you cannot clearly reconstruct the attenuation at every angle and wavelength, but you can see when it went into the Bragg condition. So, and you can do that across wavelengths, and you can reconstruct what I call as a spectral signature. So you have morphology and some kind of spectral signature. We can do that with more data. Here we have simulated some more grain data, and you can see what you're looking at is simulated neutron data as a function of wavelength. You can see that at certain wavelengths, some of the grains flicker, right? So that essentially means they went into the Bragg condition. And when you look at it tomographically, when you rotate at certain orientations, there's a strong flickering due to the Bragg condition, Bragg's law being satisfied. Okay, so once again, we've shown that we can get some high quality reconstructions. Here is a cross section from the ground truth. Here is a filtered back projection reconstruction. And here is a reconstruction using the proposed model-based approach. And this is the reconstruction as a function of wavelength. And on the top, you have from two different regions. So the outer region doesn't have any crystals. These are the single crystal region. So in the single crystal region, this is the filtered back projection. It can result in very large errors, and it's visible from the quantitative metrics as well. The summary is that by designing your algorithms well, you can allow these instruments to do more than they were typically thought of as primary use. Now, these methods are not perfect. You can have occlusion, which you may not get perfect reconstructions of the signatures. You can do a reasonably good job with the morphology, but some of the crystal signatures can be off. So the other work we have done is to improve the acquisition itself. So usually in CT, in hyperspectral CT, the measurements go, you rotate the sample sequentially. You go 0, 5 degrees, 10, 15, and so on, till you're able to complete. And when you're doing a very long measurement, it can mean that you don't get good feedback as an end user looking at what's coming out. So the other thing we have done is we have implemented an interlace scanning strategy where instead of scanning it sequentially, we jump around so that we have an interlaced scan, so that at any intermediate point in the scan, we're able to get some reasonable reconstructions. And this idea is based on a previous colleague for time resolved CT, but now we have brought this type to the hyperspectral case. And this can be very useful. So for example, we did an experiment where we have two magnetite crystals and we collect this extremely noisy data. And what you're looking at is real-time reconstructions, real-time, of course, these are very slow process because it takes 36 hours to do a scan. And what we can see is that by using a combination of the model-based methods along with this interlace scanning, we can get higher quality reconstruction. So I'll play this again to show that as these, and what you'll see on the right is the evolving reconstruction, a single cross section. And you're able to see these cross sections best or earliest for the sample when you're using an interlace scan with the model-based method. So it's useful. It's just a useful tool for end users who are using these shared instruments to have this feedback. And it is the combination of this better scanning and reconstruction that help. And here is the same image shown differently. So basically looking at the reconstruction of a 10, 20, and 30 hours using model-based methods, but acquiring the data differently. And you can see that you can start seeing the cross sections of these crystals better earlier compared to the to other scanning approaches. So by using different scanning approaches, better forward models, we can do more with these instruments, and it can make it more efficient. And often these are shared facilities. As I said, there's demand for their time. So these techniques can really help alleviate a lot of those problems and increase the throughput, efficiency, and that translates at the end to better use of money that is invested in these instruments. So that concludes the work on hyperspectral CT. I'll also now show some quick slides, some highlights about, we've been designing model-based methods for some unconventional geometries. So one example is called Neutron Laminography. So if you have a very long object and you want to scan it, the neutron beams do not penetrate such an object very well. So scientists are interested in orienting their sample differently. So for example, if you can scan, tilt, and then rotate the object, then it's a different technique. This is called laminography. So we've been developing model-based reconstruction methods for such approaches where you have low flux. And in addition, you have the usual challenges in neutrons with low flux, gamma heads, and the geometry, right? So once you have a complicated geometry, you don't have an easy there's no algorithms out there you can just download and use. So we've been developing custom techniques to allow for different forward models geometries. So once again, the forward model is similar to the previous example, but in this case, we have designed a different forward operator, which can allow for these complicated geometries. So now it allows scientists to do different things. So here is an example of some results of an additively manufactured part of cobalt chromium measured at a neutron beam line. And what you're seeing is actually the part is taped, and neutrons are able to discriminate, for example, the tape. Anyway, that's the data. And here is a cross-section from the filtered back projection and the model-based approaches. And you can see that it has lower noise, and it has you're able to resolve pores. In this case, they were interested in studying defects in the sample. So by using these model-based methods, it's easy to now be able to orient your sample differently, and that expands what you can do at an instrument compared to before. Now, we've also extended this idea to look at some cryo-EM problem. And this is, for those of you who are not familiar with the cryo-EM chain, cryo-EM is a technique for biological macromolecules. You have images collected of randomly oriented proteins, the first or macromolecules. The data is extremely noisy, and the goal is to do a 3D reconstruction from these randomly oriented particles. So the first part involves particle picking, where they go and isolate individual projection images. These are extremely noisy. Often there is a process of centering and averaging that is done to reduce the noise and find similar particles, followed by a CTF, something called a contrast transfer function estimation, which is essentially, at this point, a deconvolution-like process, followed by a reconstruction, which involves orientation estimation and tomographic inversion. So just to take a step back, it has a very much of a pre-process and reconstruct philosophy. It's very widely used. It's very popular. So we've been looking at techniques where we can say that given these noisy particle orientations, can we directly operate on these extremely noisy reconstructions. And in this work, we have basically only looked at the tomographic inversion block. So we're just leaving out the orientation estimation for this particular results I'm showing. So the main contribution is we have developed a forward model that takes into account everything like the centering, the CTF into the model. So we do the forward model. This is a single particle. This is the CTF, estimated CTF. This is the forward projector that depends upon the orientation. And this is, of course, the thing you want to reconstruct. And we also have the weighting term. So I'll emphasize that people, the differences we have is we have this weighting term, which can be very useful. Very often it's an afterthought in many applications to use a weighted least squares, but I have found this to be a very useful tool in order to address various challenges. So not just noise, but you can basically reject few pixels that are bad, which can be, again, a case in cryo-EM, because if you don't pick particles right, that can be an issue. And here is some simulated data where we have a certain structure, and I've simulated extremely noisy projection measurement. And this is the ground truth. And here we have done two approaches, the pre-process and reconstruct approach versus the model-based approach. And you can see that with the model-based approach, we're able to get much higher quality reconstructions compared to the pre-process and reconstruct for a very small data set. So we've used very few particles compared to what you might see, just to illustrate the point that these model-based approaches are robust, and that we have the capability to be able to do reconstructions from arbitrary orientations. So I'll conclude this part of the talk by a little example of yet another area we've been working on, which is cone beam CT. So these are some nuclear fuel pellets, which is made of some uranium compound, and the outer cladding is made of much lighter elements. So the goal for this task is to be able to characterize the degradation of these particles in order to build better nuclear reactors. These particles are foundational, but they're very hard to image using CT for this reason, that the core is so dense that it attenuates the beam significantly. So if I plot a line profile, you have high counts as you go here, but as you go towards the core, the counts significantly drop. They're almost zero, not quite there. And this makes reconstructing such data extremely challenging. So we've been developing model-based techniques for this cone beam CT, where we have a cost function, which is based on this. And once again, this weighting term that we have in the cost function can be very important, because it can help us treat this region of the sample very differently. So if you just plug this into a standard reconstruction technique like FDK, this kind of data, you're going to get a lot of noise because of photon starvation. If you use MBIR, the conventional MBIR techniques with the conventional weight models, you can still do a pretty good job already, right? Because it naturally weights down projection measurements that are of low count, which correspond to low counts. But by modifying the weights, you can further reduce the artifacts that can occur, for example, here, if you look. And that can be important because in this application, they're interested in characterizing what is in the cladding. So the summary is we've again been building solutions where by using these model-based approaches, we can do much more. So to summarize this section, we talked about model-based methods for hyperspectral CT systems, where by designing new forward model terms, we are able to allow for the imaging of crystalline materials. By acquiring the data differently, we are able to provide high quality feedback to users in these shared facilities, right? There are many people wanting to use it and it can be very useful. We showed how model-based techniques can help in scanning samples using non-conventional geometries, which again can be useful if you have parts which have odd shapes and you want to scan them. Having the flexibility to orient them differently and reconstruct can give you all the usual benefits of the model-based approaches along with this additional one. And we also showed how we can get high quality reconstruction for cone beam data with strong photon starvation using model-based techniques. So these approaches are very powerful. I think their adoption will increase more. And our plan is to open source the code corresponding to the previous works over the coming spring. And that's going to be called, it's a library called PyMBIR, and it implements many of these different geometries with a pretty standard prior model. And I'll leave on a note saying that we have a community of researchers, and my experience is that in order to be able to reach or translate our work so that scientists can adopt it, packaging code is very important. It plays as much as an important role as the algorithm development, so that others can try it out and evaluate all these sophisticated tools that we built. So that ends the first part of my talk. I could go on to the next unless the panel feels I should take questions right now, because I realize there are people who might want to leave because of they're in some other time zone. So Raja, should I continue or should we pause for questions? Okay, so I will continue then. Okay, so Raja?
Hey, Venkat.
Yeah, you're able to hear me, right?
Yes, there was a slight connection issue, but yeah, we can hear you now.
Okay. So I'll just maybe continue then, right? I'll just continue and just complete the next part of the talk as well.
Yeah, go. You can. There are like 3 questions in the chat, but you can also answer them in the end.
Okay,
that's fine.
Okay, so maybe I'll just answer in the end so that if people want to skip out early, they can then. Okay, so in the next part of the talk, we looked at model-based approaches. They're great. I think they're very promising technology for the scientific CT case. But in the next part of the talk, we're going to look at deep learning techniques and non-iterative techniques, deep learning techniques for doing the inversion, right? So it again goes back to the advantages of the analytic methods, that they're fast. And so these are attractive options. So in this part of the talk, I'll present some work on data-driven approaches that we've been looking at. So the first question to ask before we dive in is, when are these techniques relevant for scientific imaging? So it's a little different from medical CT or MRI, because we have to pin down when this is useful, right? These are shared instruments. People scan very wide variety of parts here, starting from rocks, to dinosaur fossils, to batteries. So when is it useful? So we've identified few areas where we think this is useful. The first one is sequences of samples. So users want to measure a collection of similar family of samples. So on the top, you're looking at meteorite rocks. This is courtesy of Andrew Needham at NASA, and they're interested in scanning these rocks using Neutron CT. So can deep learning and data-driven techniques can potentially help in this case. They can be useful in time-resolved CT, especially when you have slowly varying samples. The sample is changing with time, so that is what is time-resolved CT. So again, we can think about techniques where we use portions of the data to do some training and then use the rest of it for the reconstruction and do it fast. Yet another class of techniques we have been looking at is based on CAD for manufacturing. So in manufacturing, especially additive manufacturing, they often start with a CAD model, which is a 3D model, feed it to a printer, print the part, and then characterize it using CT. So the question is, can we use the fact that the chain of characterization is kind of unique, and we do have some data to apply these data-driven techniques. So those are some areas we think are useful. So now we'll dive into the details of what we've been looking at. So we've been looking at doing sequential data sets, what I call sequential data sets, meaning collections of similar samples. And the idea is take, in this case, one CT scan. So if you had 4 meteorite rocks, take the first one, do a conventional CT with maybe dense sampling, and then get pairs. This is a pretty standard approach. And then feed it to a neural network to train on the pairs, and then use the trained network for the rest of the samples. The rest of the samples, you would then put it to the scanner, get sparse view data, do a fast reconstruction, and then improve it using these artifact removal neural networks. And the advantage being, again, you can reduce the acquisition time, which, as I've mentioned earlier, is very important, right? When you're having scans which take 24 hours, making it a 6-hour scan can be a big deal. And so that's the domain in which we have been looking at using neural networks. Now, the data can be pretty limited. You're essentially, in this case, saying we have one CT scan. And sure, it might be paired with, with sparse view and full view data, but it's still very little. So we've been looking at 3 broad neural networks. 2 of them have been developed by Dan Pelt and colleagues. One is called the NNFBP method, which is just a multi-layer perceptron. It has very few parameters, and we use a standard loss function. We also looked at using the mixed scale dense nets, which are based on dilated convolutions. But again, they're very nice because they have very few parameters compared to at least some of the popular neural networks that are used. And these are just approximate numbers to give you a sense, right? And I'll emphasize that this network is also like a 2.5, what I call a 2.5D. So when it does 3D artifact removal, it also looks at a few slices, adjacent slices. And we've also looked at a network called AICT, developed by my colleague Amir, who's on the call, and which has many more parameters, but it's based on the popular DNCNN architecture. So let's look at some empirical results on how these techniques have been working for us. So this is an example of a meteorite where we took one meteorite scan, scanned it, retroactively subsampled it by a factor of 4, and we have pairs of low quality and high quality reconstruction. Low quality reconstruction has a lot of streaking. And of course, the reference filter back projection method, because it's densely sampled, is actually pretty good. You're looking at a cross section of the rock. And then we're going to measure the other samples at a fraction of the rate. We actually acquire it fully and then retroactively subsample to show the data. So here are results of the different neural networks on this data set. So we have the input filtered back projection from sparse view, which is noisy. You can see that it's noisy and it has all this streaking artifacts. And then here is the output of simply post-processing that with a total variation. So this is post-processed TV, and you can see it suppresses it, but it has this waxy texture. Here is the result of using the NNFBP method, which has very few parameters. It does a reasonable job, but you can see a bit of blurring and some noise still. Whereas the 2 convolutional neural networks, which is based on dilated convolution and the work that Amir has developed here, called the AICT, do a much better job in suppressing some of the noise and artifacts. And the bottom error images show something similar. So this is the error between the reconstruction and the reference being a sample scanned at using all the views in this case, because we want to conduct this study, right? So we can see that the 2 convolutional neural networks do a very good job. The MSDNet, the AICT network still has some type of artifacts, and the edge is not really near the sample. That's because this network is based on patch-based training, whereas the mixed scale dense net trains the network by using an entire images and using dilated convolution. So we've seen that at time for the streaks, correlated streaks, it does a pretty good job. But the summary was these methods worked pretty well empirically compared to the simpler neural network, of course, and they could do the reconstructions a lot faster. We also looked at how the generalization works to, at least in a simple manner, where we took the network trained to map between 1/4 sample data and fully sampled data and applied it to other view subsampling rates. And in general, of course, the performance drops compared to custom training it for that particular rate, but it still does pretty well, especially the mixed scale dense nets and the AI CT networks do a pretty good job showing that they can be used as data streams in. You don't need to wait till you hit the desired sampling rate. You're able to get a pretty good reconstruction with that. Now, the nice thing, of course, with these methods is the inference time can be pretty fast. And these are just approximate numbers. These are not optimized codes. I don't want to give some kind of impression that this is the best it can do. This is for the NNFBP and MSDNet. These are from the author's implementation, and AICT is our implementation here. But in terms of inference time, you're looking at for volumes which are for about 512 by 1280 by 1280 voxels, it can be very fast. So users can very quickly get feedback with these techniques, and they are useful when you have this type of sequential data in order to measure. We have also looked at some plant systems where, again, we have observed a similar trend that compared to the post-process TV and the neural network FBP, which does reasonable considering it's so small. The convolutional neural networks can improve the performance of these. So you're looking at the cross section from a plant, and this is the root here using Neutron CT, and we're able to get better, qualitatively better results with the mixed scale dense nets and the AICT network. And that's also borne out by looking at some of the error images here, where you can see, for example, you have some large errors in some regions, which are effectively suppressed by this CNN methods. So that kind of concludes, our studies on using these neural networks to do better Neutron CT. And for these classes of cases, it is useful to be able to do that. So the last, yep. One
simple question. What is the range or scale of these errors?
Oh, so in this case, it's relative to the attenuation window itself, the attenuation curve. So it's about, I would say about 5 to 10% window of the maximum values of the reconstruction. So the errors go between negative this thing and negative about 10% to positive 10%.
Mm-hmm.
So the scaling on these, yeah. So I'll just say that, as a note, many of these CT reconstructions in whether it's X-rays or neutrons, especially in these user facilities, they are not quantitative in the sense that these numbers can even be negative. Some of the reconstruction values here are also negative values. And it's because of issues with some of the calibration associated with the data.
I see. So I guess if it's a model-based approach, you could get rid of negative values relatively easily, right?
Yeah. So we often kind of switch the positivity constraints off in this technique when we do even model-based methods.
Mm-hmm. Thanks.
Okay. Yeah. So anyway, so I would say the take home is that, yes, these convolutional neural methods can be useful for the sequential data. And it's also interesting to look at the smaller networks like the mixed scale dense nets and the NNFBP when we have such limited data, when you have one volume to train from. These methods in the scientific case, which might be very well the case in a lot of these scientific CT applications. These can be as competitive as having to train the AICT or bigger neural networks for this application. So the last examples of bringing these neural network or data-driven techniques, as I said, is related to a CT for additive manufacturing. Again, where you have a CAD model, you print something, and then you want to scan the part. And often when you're looking at metallic parts, you have a lot of challenges, like there's scattering, there is beam hardening that can occur, in addition to the noise and streaks that you might see when you try to make the scan fast. So the question is, can we use this? And I'll say that this is preliminary work. And so our approach on this point for this class of problems has been starting with a CAD model. We need to make realistic looking, we're going to generate realistic looking data. So we have a defect generator followed by a physics-driven simulator, which can simulate things like beam hardening, noise, and we're going to generate a lot of simulated data and then train reconstruction algorithms to go from the simulated, noisy projections, do a standard reconstruction, and then map it to the target we need. And then the goal is to check how well can we transfer that, which is purely learned on simulations, to the real data itself, right? So that is the hope. That is the
holy grail. If we can get that to work, you can imagine that a manufacturing floor, which is making a certain class of materials, once they have a CAD model, they can train these networks and have very nice reconstruction engines available to them. So here are some preliminary results of cross sections from reconstructions of a jet engine turbine blade. This is all simulated first. So here is the ground truth. We had some data generated, and this is the model-based reconstruction methods of the first part, which are time-consuming. And when you have put in more sophisticated models, in this case, we do a two-step beam hardening correction and then reconstruction. It does a reasonable job, but with these neural network techniques, we can get a pretty good result, again, from these sparse view data sets from the CAD models. But this is still, of course, all simulated. And if I zoom in a little bit and start looking at some of the cracks, we see some blurring, but we also believe that maybe we need to adjust the parameters a little bit for these model-based methods, regularizing wise. But both the mixed-scale DenseNet, which is based on dilated convolutions, and the patch-based neural network do a pretty good job. In this case, we actually were observing that neural networks trained with smaller patches, we were able to resolve some of the tiny features better in this case. And then we, of course, applied it to some real data. And our observation has been that, so this is what we see, a real jet engine turbine blade that we scanned. We use the networks that we trained purely from these CAD models. This is the analytic FDK method, which is fast. And then this is the net outputs from the neural network. Now you can see that it clearly clips or rather forces the value to be positive. That's because of the nature of the CAD model training. And, but in this case, we can see this crack that we think is pretty nicely reconstructed, but we still have some ways to go, right? So in order to verify how good are these creating some false features, and I'll end on a note of caution, right? So when we have to deliver something like this to people using this as a tool, there's still a lot of work that has to go in to verify that are these methods producing the right answer? Are these cracks real? And that is an ongoing effort for us here to improve the simulation. But we think this is promising, that as we push this, if we are able to make it work, this can be a very different way that people think about doing CT scans of additively manufactured parts in a shop floor. So in order to summarize this little part, it's about applying neural network techniques to collections of samples and time-resolved Neutron CT. We see that it can help push the overall scan times and get fast reconstructions. For the small data sets encountered, the smaller neural networks are pretty effective. And we're investigating CAD-based models to do CT reconstructions, so to enable fast scans and also deal with all the various challenges that can occur, like beam hardening and scatter. So that concludes my talk. I'll end with a few from us different backgrounds here, and they're looking for interesting challenges. One of the challenges that exists with all these methods is automated parameter selection. And that's still a little bit of a challenge in terms of that, people need to get around this too, so that it's widely used, right? So when there are papers written in big journals like Science, Nature, these class of techniques start being used. And there's still, that is one of the challenges. We need to design instruments with better feedback control so that we can acquire the data smartly. How to deal with deep learning in these cases, because you have widely different categories of samples. So the first could be a category of rocks, the next could be a category of dinosaur fossils or something. So how do we tune these methods to deal with different categories of samples? And then how do we improve reconstruction speed to deal with large detectors? So these are some big, broad challenges I see in this area. So with that, thank you very much for your time. And thank you for everyone who signed in. I'm happy to take questions now.
Okay, thank you very much, Venkat. So we have several questions. So the first one is from Ulukbek. So I opened for you the mic if you want to ask a question.
Hey, Venkat, thanks for a very cool talk. I had actually a couple of questions, but I'll go with the first and maybe we'll come back if other people don't have too many questions. So the first question I had was about reconstruction quality that's expected, right? You showed a lot of techniques with different levels of reconstruction quality. So what quality is good enough for end users you talk to? And do we have actually any understanding of that? What's required?
Right. So that's a very good question, right? In the sense, like, what is the end goal? So I've seen two kind of categories of users. So some people are trying to make a measurement, right? So what is the porosity of a rock? So the end goal is to determine, I need to find how porous or how many pores or what fraction of the material is porous, right? For these people, I think the quality is often defined just by that end goal. So how accurately is it doing that task itself, right? And then there is the other category where they bring one-off samples. There's just one unique sample, like some scroll, or some historic artifact. And there, the notion of quality for now is actually, it's pretty just visual quality. There's no objective metric that seems to be used for many of these cases. In fact, when you look at the method section of a paper written in maybe a like a high impact factor journal and look at what was done, there's not a whole lot of discussion about how, for example, even for filtered back projection, how was the parameter tuned, right? It's often done still visually so that it's low noise and fairly sharp. So I think there is some work. There's still some open questions on that field. For now, it's going in this mode where visual quality is the prime thing, and I think there's more work to be done. In fact, I think in one of the earlier seminars when Katie was talking and discussing how much work went into actually verifying their method. So something of that rigor is not done in routine scans, is what I've seen.
Thank you.
Another question is, in which practical application this work will be useful in limitation of your algorithm?
So in terms of, in terms of practical applications, I think the first part, and both these techniques can be used, and they have been used in instruments at Oak Ridge as well, right? So it is used in practical applications like Neutron and Xray CT to accelerate how fast you can make the measurements. And that can be a big deal. So the practical applications are the ones I've listed here. So that I spoke about, right? So now, if you mean practical applications outside the scientific imaging realm, so they're useful for other X-ray CT or other inverse problems associated, like MRI, CT, ultrasound as well. So I'm not sure whether that answers the question or whether I fully understood what you meant by the practical applications.
Okay, and maybe the second one is about limitations. So what limitation, where it would fail, or?
Yeah, sure. So in terms of limitations itself, these methods do involve choosing parameters. So that is still, it's not such a, I don't want to make it sound like it's a roadblock, because any algorithm has a parameter, but I think there is, as a user community, there is a level of, I think, education about these methods that needs to happen so that they can be adopted more widely. And understanding what that parameter means is a little more complicated in model-based techniques compared to like a filtered back projection, right? Because the noise resolution properties can be impacted. It can also be. So that is a challenge. Communicating that and understand it is one of the practical challenges. And then computational complexity is a challenge. So especially in the first half, researchers have been pushing how fast you can do these reconstructions, but it's always a cat and mouse game. So detectors are getting bigger and there's always like more work to be done. But I would say from a practical point of view, reconstruction speed on compute resources that are easily, that one might have, is a major challenge.
I think Uluk Bek has another question.
Thanks, Rajay. So I had one question about this end-to-end reconstruction with 3 types of neural networks that you use. I think it was slide 39.
Yep.
So basically, there seems to be a trade-off between the size of the parameters, the size of the training data, and then finally inference and training times. So can you make any kind of conclusive remark? How should we proceed if we face a similar problem? So do we want to go to a smaller network, larger network, or how would we decide?
Right. So I will say, like, out of the kind of cases where I've looked at, I would say the smaller networks are pretty impressive themselves, right? So but it could be that we have such limited data, like when you have just one CT scan. So I think my answer to that would be, do look at the smaller networks as well, right? So often the mixed scale dense nets and the NNFBP, I think some of the other networks have become really popular, the very large networks. So I think the take home would be also try these smaller networks and evaluate for your application how they're working. They can be, my experience is they work pretty well as well. So yeah, and, but I don't have like a good guide on how to choose, for example, the network parameters. So for both these networks, I chose somewhat what was default. That was used by the authors, and it was that were orders of magnitude different, right? So this network is orders of magnitude smaller than this one, and one on the right, which is I think one of the more widely used architectures, has many more parameters. So I think it is interesting to push the number of parameters down and see how low can we go and still get pretty good answers.
Sounds good.
I would like to add something to that as well. Like in this study, we were looking at using a small data set for training this network, and like a smaller network, we hope, like we knew that they work better with the smaller data set. And one of the things that we noticed, like something like a deeper neural network like AICT, that one also performed very well, despite the fact that we had a very small data set. That's something also to consider. So it's two ways. Like one way, like these networks are very good, but with the smaller networks are very good with a small data set, and maybe they are practical if you want to start with them first, which is fast. But at the same time, we cannot say because we have limited data set, we cannot go to deeper neural network and use them.
Cool. Thanks. It's good that it's coming from the inventor of 2.5D.
So we have another question by Greg. So I will open the mic for you if you want to ask.
Hey, Venkat. I was just wondering what kind of priors you use for the hyperspectral imaging. Yeah,
so for now, that's a good question. So I kind of skipped over the point about the priors. For now, we have used just, we have not used cross-channel priors. The priors are just single channel for the hyperspectral. But I think that is another area where there is a lot of scope to improve those prior models. But for now, they're Markov random field-based priors on single channel. So I haven't used cross-channel priors for this work.
Okay, thanks.
We have another question by Sundaresh. I will open for the mic as well.
Hi, thank you, Venkat. That was a really good talk. I think my question is like very similar to that of what Modelbased was basically asking initially. I was just wanting to know, because you did say that you have a lot of end users basically who come to you in terms of using these machineries and you do the reconstructions, right? Yes. Have you had the chance to actually talk to them as to what is the end goal? Have you actually, because that could actually help in terms of doing something like task-based image quality evaluation, right? As compared to visually looking at it and looking at the other metrics like MSE and other stuff that you've been looking at. So have you had the chance to?
So I think, so Sundaresh, I think I don't have results on it, but I think there is the answer is, I think people are realizing that this is needed. So for example, so the answer is not yet in terms of we have not done anything, but as a community built around these kind of, CT for scientific instruments, they've in fact put out a little challenge where we have more task-based evaluation, right? So there was an example of a data set where we wanted to evaluate porosity, for example, just porosity. And then how much improvement do we get with these methods if we do sparse data acquisition? So it is starting to happen. The conversation is being built. And I think one of the first ways to address this is to create data sets where people can then, so that is starting to happen already. So hopefully over the next year, we are actually able to not just use the RMS EPSNR, but also have more task-based. But I think that's a huge, there's a huge opportunity in that space for the scientific imaging, right? So I think that's one of the great successes of a lot of the other fields in computer vision has been creating data sets with some task-based objectives. That has not happened in this world yet, but it's starting, the conversation is starting to happen. People are willing to share their data. And so I'm optimistic that over the next year or two, there'll be more results based on that, and then evaluations based on those techniques.
Okay, thank you.
I had a question.
Yeah.
So Was it Amir who was saying about in some of these applications that the training data may be somewhat limited?
Yes.
So, yeah, so it seems like, so have you looked into probably extending the plain neural networks to something that's more hybrid that may make more sense with limited data?
So, Amir, do you want to take that?
I am not sure if I understood the question correctly. Sorry, I wasn't paying.
So my question
yeah.
was, by hybrid, I mean like something that's a combination of model-based and you know, a deep
Yes,
neural network.
yeah. So we talked with Venkat about it quite. We haven't tried it. We talked with Venkat about it. So far, the way that we handle limited data, we tried data augmentation. So we use data augmentation to for the large network. But yes, we have also talked about like somehow using it in a plug and play format, for example, that we use this as a prior model. But no, we haven't done that, but we have planned some stuff.
Sounds good. Thanks.
I have another question. So you use voxel representation in all your work. Did you consider using point cloud or mesh or other more efficient representations for 3D? Is it possible to use it with the things you scan?
So not for this. We've not used different representations for now, but I think there are applications, especially with when you start looking at arbitrary, orientation-based CT, and it's not simply things rotating around a single axis. There are works people people have looked at using like blobs and spline representations, because it can make some of the implementations much easier if you have rotation radially symmetric things. But I have not, and I think that can be important too, especially when you start looking at different geometries. So Raja, the answer is no. There is some literature for sure over the years where people have looked at different representations in certain areas, but in this work we have not used that. We just used the voxel basis.
And another question I have is, what is the largest gap you found between simulation and actual scanning? Because many times we try to claim we do some CT experiments in simulation and then you do the real scan. So the question is, how big is the gap, or is it real gap?
I think that is most relevant to the last part, where we are trying to build this simulation engine. And so for now we've been trying to close the gap. I don't know, Amir has worked on a lot of details of this and done very careful evaluations of how the simulated data looks compared to real scans, because we have access to the machines.
Yeah.
So initially, it took us some time to figure out what all needs to be put in, I think. And even now, I would say, Amir, do you have more?
Yeah, the thing is, Evan, like we try to calibrate the sample carefully. We try to find, for example, the beam hardening parameters for these samples. But then getting the scatter right, for example, the physics is quite challenging. So we try to simulate that, but still, or also the texture of the noise with what we are approximately modeling compared to what's really happening in the real measurement. That was also something. And we have been looking at domain adaptation technique and wave the scattering coefficient between real measurement and simulations to see where are the differences, identify these differences, and find way to include that into our modeling. And that's something we are doing.
Okay, thank you very much. So thank you very much for this very interesting presentation. If anyone else has questions, so please ask now, or be silent forever, or just send mail to Venkat. So thank you very much for attending and for the very interesting presentation.
Thank you all. Thank you for the organizers. Thank you for those who signed in as well. Thank you. Bye-bye.
Bye.
Thank you
Thanks,
very much.
Venkat.
Bye.
Bye, Amit.